Brute force optimization has the signal benefit of guaranteeing the universally correct answer. Many problems, however, are too computationally difficult to calculate all variations of approaches to get a solution. Some of the salient differences in types of optimization problems include discrete versus continuous. Now, a moment ago, you considered a discrete problem, or a problem that's broken into unrelated chunks. This was the coin problem, or the password problem. Both of those problems are distinguished because each answer is separate from the other answers in a mathematical sense. Continuous problems, like these functions that you see in this diagram here, are problems that at every point they have a definition. And so when you have to scan them using a brute force method, you actually just have to check points that are very close to each other across the entire range. Another salient difference is convex versus bumpy. So here we see a smooth convex function on top. If you needed to optimize this function, it behaves pretty well. You know that if you find yourself at a point that is rising in one particular direction, if you pursue it in that direction, sooner or later, you will reach the maximum. The bumpy function, on the other hand, has many local maxima. And if you're trying to maximize the problem, it's even worse to look at things that are near -1 and +1, where you have values that are almost as good as the true global maximum at 0, but not quite. The relative size of the problem is also critical. For most of these problems, the size of the problem rapidly becomes prohibitive for brute force approaches. This necessitates the use of what are called heuristic methods, which are methods that attempt to use some kind of rule of thumb to rule out bad answers, invalid categories of answers. And they let you target your search to a particular part of your candidate solution space.